It's our
We're live in 3, 2, we are live. So welcome everybody. Today we are very excited to have Hongjun and Jiwon from the Seoul National University present their ICCV 2021 paper, Separated Softmax for Incremental Learning. Hongjun's a PhD student and Jiwon is a master's student. They're both located in Seoul. Thank you so much for presenting at such a late time for you tonight. So yeah, we are very excited to hear your talk, and without further ado, please go ahead and take it away.
Okay, thanks for the...
I can't hear your... I can hear you now.
Okay, hello. Thanks for the introduction. Hello, my name is Ji-Hwan, and I'm right now with...
So yeah, we are very excited to hear your talk, and without further ado, please go ahead and take it away.
Thank all the members and thanks ContinualAI for organizing this seminar. We've done this work a year ago and published it in ICCV 2021.
I can't hear your... I can hear you now.
Okay. Okay, so this is the outline of today's presentation. First, I'll explain about the background of class incremental learning, then its recent methods and related works. Then I'll explain the motivation of our work. Then Hongjun will keep on explaining our method and experimental results. First, class incremental learning assumes a scenario where numerous data are received sequentially and where full availability of all training data is impossible. So, at the training time, it learns to classify new object classes from incrementally arriving training data. So for example, let's say a single task is a classification task which learns to classify two classes. Here, the training data for task 1, D1 arrives and is composed of two classes, which are cat and dog. From now on, we use C1 as a class set of task 1 and D1 as training data for task 1. So after the model learns task 1, new data for task 2, D2 arrives. Now the model learns to classify the new classes, which are now bear and lion. So here, as you can see, the training data for all tasks are not available. Only D2 are available. So this sequential scenario continues until we see the last task. So on the other hand, at the test time, the model is expected to classify all the scene classes. So let's say after the model learns task 2, an evaluation dataset, which is composed of all the scene classes, comes to the model, and then the model is expected to classify all the scene classes. So the model has to classify between the cat, dog, bear, and lion in this case. However, since the model can see only current dataset, the performance of previously learned tasks degrades, which is called catastrophic forgetting in class incremental learning. So as you see in the figure, the model is able to classify the lion image, which is actually the new class, which is the new class, and however, it fails to classify the cat image, which is actually for the previous task. Using knowledge distillation and small subset of previous data are simple but currently effective methods that has been used to solve catastrophic forgetting. So now I'll explain the two methods that has been used widely in CIL. First, exemplar memory is quite an intuitive method. Other than using only current available data, it uses exemplar memory that holds small subset of old data. So as you see in the figure, at task 2, the model learns D2 along with the exemplar memory. So this exemplar memory holds some classes that are in D1. However, there is a critical disadvantage of using exemplar memory, which is called prediction bias. Since the memory is quite small compared to the D2 currently available dataset, the dataset is severely imbalanced. So it induces imbalanced prediction score, and finally it results in prediction bias towards the latest task. So in the figure, it shows the prediction results of simply fine-tuned modeled in CIL. This CIL scenario was composed of 10 sequential tasks, and this figure shows the prediction results after the final task, which is 10. Oh, sorry. So the y-axis shows the true task number of the test data set, and the x-axis shows the predicted task number. So the darker color in the 10th column insists that the prediction was towards the latest task, which is task 10. The second method is knowledge distillation, and it was used in CIL to overcome catastrophic forgetting. For those that are new to knowledge distillation, I'll briefly introduce the concept of knowledge distillation. So the basic concept is that it distills the knowledge of large pre-trained model to the small student model. Technically, the knowledge is said to be transferred by training the student model with the soft target, which is the output softmax of the teacher model. So in classification test, the student model is doing cross-entropy learning with a soft target instead of the one-hot label. So let's assume the model is learning the third task at class incremental learning with the exemplar memory and the new data set, which is D3. So the ordinary just cross-entropy loss affects the scores of the older classes C1 to C3, and the loss for knowledge distillation only affects the classes for the old tasks. So the model learned at previous task becomes the teacher model, and the current model at task 3 becomes the student model. And the current data with exemplar memory is given as an input for both teacher and the student. And then the output softmax of the teacher model is used for knowledge distillation. So this enables to distill the knowledge of previous test model on using the current data set. So I think you guys are quite new to this concept. And then now we will explain the related works that have tried to solve both the catastrophic forgetting and the prediction bias, which was caused by the exemplar memory. First, end-to-end incremental learning, EIL, try to solve the imbalanced prediction bias by using the class balanced data set. So after it trains the model, it just fine-tunes the model. It fine-tunes the model with the class balanced data set. So this class balanced data set is composed of data set and the number of data sets for each classes are the same. So that's why it's called the class balanced data set. So after it balance fine-tunes with this data set, the prediction score for all the classes becomes quite even. Second method is called BIC. Unlike EIL, the BIC additionally trains a linear model to correct the bias with the class balanced validation set. So it's quite similar with EIL in terms that it uses the class balance set, but this method rather trains the linear model that scales the final scores of the model. So after training the model, it additionally trains the linear model to scale the scores to make the scores quite even. And lastly, it's called IL2M is IL2M tries to rectify the bias prediction probability with safe statistics. To make long thing short, it's quite similar with the previous method, the BIC. It also scales the scores by the statistics obtained when the classes are initially learned. So our work, the motivation of our work is that to try to resolve the root cause of prediction bias. Since the prediction bias was caused by the exemplar memory. But unlike other previous methods, other than post-processing, we wanted to analyze the root cause of the bias and alleviate it while training in an end-to-end solution. Second, previous works use KD in different manners without any comparison or justifications. So in this paper, we point out the two different use of KD in CIL, which we call general KD and task-wise KD. Difference is in the normalization range of the softmax. So for softmax, GKD normalizes between all the classes seen in previous tasks, and TKD normalizes between the classes per each old tasks. A year ago, when we were working on this, previous works either use KD on its own perspective, and surprisingly, they did not quite compare its use and its effects. So, for example, like the work called Unlabeled first note the difference, but they did not analyze the use of KD in CIL, and IL2M and Scale even insisted that KD should not be used because of the prediction bias. So in this work, we wanted to experimentally compare the use of KD in CIL.
So for now, I'll explain our method. Our method is called Separated Softmax for Incremental Learning, which is also called SSIL. First, we take analysis. So as Jiwan said, our analysis is that the root cause of the bias is on the gradient for the output score. So especially this gradient is for the output computed from the ordinary softmax. So the equation in the middle means, okay, here, the equation in the middle is the gradient with respect to the logit Z, TC. So the T means the task identifier, and the C is the class. So for example, for example, the P is always less or equal to 1. So if the C is ground truth label, the gradient is always negative. And if the C is not a ground truth label, the gradient is always positive. So we explain our work based on this gradient. So let's consider the gradient descent on logit Z TC. So as I said, when C is ground truth, it has a negative gradient, so the logits can be increased. So this is very simple notion, and vice versa. If C is not a ground truth label, the logits can be penalized. So I will give you some example. So here, this image is for the line class. So that means this image is for new classes. So when this image propagates to the model, the scores for lion is getting increased, and the logits for other classes are penalized. And this example is for the image of old classes. So similar as previous slide, when the image for cat class is propagated to the model, So the logits for all the classes is increasing and other logits are penalized. So this is very simple example. So now we think that, so we in CIL, to prevent the catastrophic forgetting, we said various methods utilize the exemplar memory, but that means we always use the imbalanced data set. So here, so DT is always large and M is always small. So we use imbalanced data set. So therefore, the samples from this imbalanced data set is always imbalanced. So that means we always use the imbalanced mini batch. So because in this mini batch, the majority is the samples for new classes. So that means the minority is samples for all classes. So the gradient value for all classes are mostly positive in imbalanced mini batch. So as a result, the logits for all the classes can be already penalized. So this is because of the abundant samples of new classes. And we also find additional problem on using knowledge distillation. So as Jiwon said, recent methods utilize the knowledge distillation to prevent the forgetting in CIL. And there exists two kinds of knowledge distillation. And in this case, we handle general KD, which is also called the GKD. So here, the GKD use the softmax that is normalized by all the old classes. So based on our analysis, the Z softmax can also be biased toward the latest new tasks. So the latest new task for teacher model is old classes for student model. So when we use this biased softmax, this part of student model can be biased. So our main objective of using knowledge distillation is prevent catastrophic forgetting. But in this case, when we use GKD, we rather preserve the bias, which means it rather induce the catastrophic forgetting. So as we said, the fundamental problem is on the softmax. So, and this is because softmax is normalized by all the same classes. And we said it rather penalize the logits for all the classes. And for now, we introduce our solution. So our solution is very straightforward. So we just separate the softmax to remove the penalization of the logits. So here, though we use the imbalanced mini batch, because we separated the softmax, each part, so this part and this part is for old classes and new classes respectively, but they do not hinder each other because they are separated. That means the gradient for this part is exactly 0 when we propagate the samples for new classes. So here we give a comparison between SSIL and ordinary CE loss. The upper figure is for SSIL. So as we can see, so for now, they do not hinder each other. So we can train each head separately, and there's no biased logits anymore. But in ordinary softmax, the logits for new classes is always biased. And our second solution, so I'll note that this is not a novel solution, but we adopt this through our analysis. So with similar intuition with SS, we instead use a TKD. So I'll explain that. So when we use GKD, the softmax or GKD is normalized by all the other classes, but when we use TKD, the softmax is separated by each old class, each old task. So this softmax do not have any biased probabilities. Here, this is our final loss function. So our loss function is LCSS, which means we combine the separated softmax with cross entropy. Here, so this loss is the cross entropy loss, but it is only for all classes. So I'll explain about the notation. So here, the 1 to t-1 is it only considers the old tasks. And here, notation t means it only considers the new classes. And this is an indicator function that when the ground truth label is in the set of old classes, we only compute this loss and vice versa. So this perfectly separates the softmax between old and new classes. So this LSSIL is our final loss function, which combine with LCSS and the nullity distillation loss. And as we said, we used the TKD loss. So now I'll present our experimental results. So first, we think about the essentials in evaluating a CLAI model. So there are two parts. The first, in CLAI model, the evaluation has to be handled in large-scale benchmark datasets. So we think that realistic image recognition tasks handles large number of images and large number of classes. So in small-scale dataset, we think that just retraining the model may be more practical. So we use two kinds of datasets. The first one is ImageNet with 1,000 classes. And the second one is Google Landmark version 2 dataset. So it consists of about 200,000 classes, but we sampled 1,000 and 10,000 classes based on the number of images per classes. And the second part is we evaluate our model on diverse incremental scenario. So the objective of this evaluation is to show the robustness of the model in various scenarios. So it consists of 3 scenarios. And here, so training data is either ImageNet or Google Landmark dataset, and we separate that dataset with equal number of samples per task. And the variation is the number of samples per task. So for example, in this case, the number of classes per task is about 100, and that is 10% of total classes. And in this example, the number of classes per task is about 50 classes, and this is almost 20% of total classes. And the second variation is we used small or large memory exemplar. So for example, storing 5,000 samples or 10,000 samples, etc. So this figure is our experimental results. So we evaluated our model in 10 number of classes, and we stored 20,000 samples for 1,000 classes dataset and 60,000 samples for 10,000 class datasets. So here, the ImageNet 1K and Landmark 1K consists of 10,000 classes, and Landmark 10K consists of 10,000 classes. And here, the x-axis means the number of classes, the number of scene classes. So for example, the classes 500 means we train with our model with 500 scene classes, and the training procedure is performed with a sequential manner. And at this time, we evaluate our model, and the metric is top 5 accuracy. And I'll explain about the legends. So first, the upper bound is the results for joint training. So this model do not handle any forgetting, or so this is not a continual learning model. So this is trained with all the classes. And this is for baseline, and the accuracy for last class is here. And this is for our model, SSIL. And we can see that the SSIL outperforms all the baselines in all scene classes. And the second result is the top 1 and top 5 accuracy for all the evaluation scenarios. So as we said, we varied the exemplar memory size with fixed number of tasks, and we vary the task scenario with fixed exemplar size. So in this evaluation scenario, as we can see, SSIL outperforms all the baselines in most of the scenarios. And there are some interesting points that when the model is trained with lower memory, the accuracy drop of SSIL is much lower than other baselines. So for example, when we store the 20,000 samples, the top 1 accuracy, so this top 1 accuracy is the average of top 1 accuracy. So this is not a final accuracy. So for example, in this case, the performance degradation of SSIL is just 0.7%. But in case of POTNet, LUCIR, or BIC, the gap is much larger than SSIL. And this phenomenon is also can be seen in average top 5 accuracy. And we carry out additional experiments. That is, we also consider the training a model with large base classes. So that means the number of samples and classes for first task is much larger than other tasks. So here, so this small base class is a evaluation scenario for previous results, and this large base class is a new experiment scenario for us. So in this scenario, we can utilize rich information of the features learned from the base classes. So that means because the first task has much larger number of samples, we can utilize the features from the task 1. And recent methods, for example, LUCIR or POTNet, adopted this scenario, and they use explicit laws for feature preservation. So for example, they use kind of knowledge distillation loss. So that is prevent the features from going away from the previous text. And here, this table is for results with large base classes. And in this case, SSIL also outperforms in this scenario. So especially SSIL outperforms LUCIR and PONNet. And we note that we didn't use any explicit loss functions on the features. The next experiment is analysis on prediction score. So here, these two figures are about the average score of output score, and the right figure is top 5 accuracy for various models. So here, the x-axis is number of scene classes, and here, the bold line represents the score for all the classes, and the dashed line means the score for new classes. And I'll explain the 4 various models. So the first one is our SSIL, and the second one is SSIL without SS, so which means we used ordinary cross entropy loss with TKD. And third one is training SS and without TKD. So that means we only used the separated softmax. And the fourth one is a vanilla model. So it is trained without SS and TKD. So this experiment is to show the effectiveness of SS. So we ablate the SS, and we can see that, so here, when we use the SS, the average output score of old and new classes are exactly 0. So that means there is no score bias anymore when we use separated softmax. But when we use just ordinary softmax, the output score for new class is much higher than the old classes. And this okay, so and when we remove the TKD, the phenomenon is just same as before. And this experiment is to show the effectiveness of TKD. And here, so we'll compare the blue line and green line, and as we can see that when we remove the TKD, the accuracy drop is large. So this means that using knowledge distillation is very good at preventing catastrophic forgetting. And this is our last experiment result. So this experiment is evaluating on fine-tuning model with using GKD or TKD. In this example, experiment, well, we did not use any bias correction methods. So we only used the variant of knowledge distillation. In here, the left figure is top 1 accuracy, and the right figure is top 5 accuracy. And we can see that the accuracy of using TKD is much higher than using GKD. And we think that this is because TKD use separated version of softmax. So the teacher model, the softmax of teacher model is not biased. But when we use GKD, the softmax is always biased. So here are our conclusions. So first, we analyzed the root cause of the prediction bias, and we did some extensive experiments on large data set with various scenarios. And using a simple modification, SSIL outperforms the baselines. But we think there are some drawbacks. So for example, SSIL is not an optimal solution for blocking the gradient from the new classes. So this is just intuitive solution, not an optimal solution. And the second one is our loss function has no explicit term for distinguishing between the old and new classes. Okay, so that means because we separated the softmax, the model has no ability to classify between the old or new classes. And here are the references, and thank you for hearing our presentation.
Great. Making sure I don't hear playback from myself. Yeah, so that was a wonderful, outstanding presentation. First, before we go into questions, I just wanted to state here that I think that the first half and the motivation slides, especially, were just an outstanding survey of class incremental learning and the bias problem in general. You've seen this come up in many works. The one I first think of is the large-scale incremental learning paper, but they're all attacking the same issue, and I feel like your presentation did a very outstanding job of unifying those concepts with your clear figures and showing how each of them present it in a different way. And I think even just that part was a very, very good contribution. And then came your method. So I thought that was a great presentation. I wanted to say now, if anybody has questions, either please ask them on Microsoft Teams, or you can put them in the YouTube chat if you're watching live. There is one question/clarification that someone has asked in YouTube. They're asking just, in task incremental learning, can you say separated softmax is already happening there? Because in task incremental learning, you are already doing cross entropy wise by each task individually. And yeah, none of their heads, yes, that was my intuition too. This is more focused on the incremental learning, the class incremental learning, where people are doing the generalized distillation. Does anybody have any questions at this time? I'll go ahead and start with one. So I think your method works very good, given my intuitions of incremental learning. It makes sense exactly and precisely what you did. I'm wondering if there is one assumption that your method needs, and I just wanted to ask your opinion on that. From my intuition understanding, I think that this only works well when you have large number of classes in each task. That is, for example, if you had very small task sizes, you would struggle because you'd be only able to learn cross-entropy loss over a few set of classes, for example. So I'm wondering, is that kind of true? Do you think, did you try your method on like small classes per task and see how that worked? And I'm just wondering what your intuition on that is.
Yeah, so as you said, we did some experiments. We also did some experiments on small data sets, for example, CIFAR 100, and our result is very poor because it only handles small number of classes and small number of samples. So it does not work. But in large scale data set, it performs very well.
Yeah, kind of like our work started from thinking that the class incremental learning experiment should be implemented on the large data set. So at first time we didn't consider the small data set and didn't think about the disadvantages of our work in small scale data set. But later we figured out that this might not work, as you said, in small data set also.
Yeah, but that makes sense. I mean, I think most methods, a lot of them have been developed for CFAR 100 and then applied, whereas you did the opposite, and they're both. I mean, if we think about large-scale applications, the giant data sets is where we want to go. And so I did not mean that as a criticism. I just want your input on that because I don't think not being able to downscale is really a problem. Awesome.
So we thought, so we thought that if we could handle the explicit term for the old classes and new classes, that might resolve the small-scale dataset issue.
Yeah, I wonder if you were able to introduce the bias layers from the large-scale incremental learning BIC paper. I wonder if something like that could help, but that's, I mean, there is no point to try and do that for the small data sets if you already had something that works very well on the large scale. So, great. I'm looking at YouTube chat. Are there any more questions, or does anybody who is on Microsoft Teams want to unmute and ask a question? It looked like maybe you're unmuted, Elaine.
Yes.
Yeah, perfect.
Just want to ask, like, I'm not sure whether I fully understand your method, but is it you distill this loss on the same model, or you using different model?
You mean like the
architecture, like you train the old class in one model, and then the new one in another brand new model, and you distill the loss to the new one.
Actually, we just trained only a single model, and we just separated the output layer. So we use a single model, and there is two classifiers. But at evaluation time, we combine the two output layers and give a prediction.
Okay, so you mean you in a single model you have two separate classifier,
right?
To handle two separate like a softmax, right?
Yeah, but that is only for in training time.
Okay, thank you.
Thank you.
Any other questions? At one point you mentioned all of this has to do with imbalanced batches. I wonder, did you look at, and this may actually, now that I'm starting to say this question, it probably does not make sense for the large scale data sets, but focusing on balancing from the data side, like making your data loader such that the classes all appeared equally and showing, I would expect your method to work much, much better than that. But I was wondering if you specifically looked at, since you talked about the issue from a data loader bias kind of perspective or imbalanced batches, if you looked at artificially creating balanced batches using your core set or not.
So you mean that when we sample the mini batch, we artificially give a balance on old or new classes. So is that?
Yes. Yeah. Yes.
Actually, our original work was based on that. So we first tried the balancing the samples between the old and new classes. So, and we vary the ratio. So I mean the 1 to 4, 1 to 8, and at that time it works, and it performs very well when this combined with separated softmax, because when a model, when a sample is given, the old samples are dedicated to only the old classifiers, right? So it was very well. But when we combine this model with knowledge distillation, the effect of the balanced batch is vanished.
It kind of reduced. So like with the knowledge distillation, we also have that result in the supplementary materials, and we compared with the mini batch with the same ratio and the one with the mini batch without the same ratio, but those both results showed the same results.
Yeah.
Okay.
Absolutely same result.
Great. Okay.
Yep. Yeah, but there are some results about the balanced mini batch in our first version in archive. So you can see these results.
Right, and even if it did work as good, I would imagine that a method that does not need that should converge faster, because I would imagine to get the balanced mini batches, you'd end up needing more samples from a data loader, and theoretically we are looking for computationally efficient methods. So even if they perform similar, I would imagine your method would converge much faster to an optimal solution. Great. I do not see any more questions in YouTube. Last chance for questions on Microsoft Teams. If not, I think this will be a good time to thank you so much for your presentation. Thanks everyone to joining, and especially you two for presenting today. You can catch us here again next week. We'll be back to our normal time at 17:30 Central European Time, and we'll hear a presentation from Freya Akirak on the work Subspace Regularizers for Few-Shot Class Incremental Learning. So thank you, everybody, and we'll see you again next week.
Okay, thank you.
Thank you, James.
I think we're done if you want to